Hey guys, we are citizen scientists who work with the Globe Mosquito Habitat Mapper and land cover datasets.
I'm Prachi Ingle.
I'm Mateo Kimura.
And I'm Pratham Babaria, and we all worked with Rusty and Pater this past summer through the NASA SEAS internship. Through this program, we grew familiar with the Globe Observer API, and together we explored and evaluated the Globe data quality and accessibility.
Here, we've outlined our overall process. First, citizen scientists are trained to use the Globe Observer app to conduct guided observations of mosquito habitats and land cover in their local areas. Then, the Globe Observer app processes and stores the raw user data in the publicly available Globe database. The yellow box is where we come in. We created a Python procedure where users pull data from the Globe API. They can filter by their protocol like mosquito habitat mapper or land cover, date range, and location. We then go in and clean up their data, removing redundant information, establishing logical naming conventions, and standardizing reported data so that null values are the same across the board, and there is only one value per column. After cleaning the data, we then added quality assurance flags, summarizing the data for future users to better visualize their data quality. We also began ranking data observations by their usability. To do this, we created a completeness score that shows the user how much key information a specific observation can provide, allowing users to quickly filter out observations that lack key components. We then provided diagnostic graphs for users to quickly visualize their data sets. Lastly, we created an algorithm for users to choose specific criteria for the dataset prior to download. For example, in the mosquito habitat mapper datasets, the users could filter out observations of a specific mosquito genus. Ultimately, we plan to implement these pre-processing procedures into a new beta vetted data access portal. This would significantly increase the accessibility and usability of Globe's rich citizen science datasets, encouraging future citizen scientists to engage with our data for their own scientific questions. What are some problems that we found in the datasets? Sometimes the column names were not very intuitive. For example, in both the mosquito habitat mapper and land cover datasets, there were two sets of location data: measurement latitude, measurement longitude, and just latitude and longitude. The measurement latitude, measurement longitude values matched the GPS coordinate system, while the latitude longitude columns followed the military coordinate system, MGRS. So to reduce confusion, we renamed these columns to latitude and longitude and MGRS latitude and MGRS longitude respectively. We also found that some columns were redundantly homogeneous since all the cell values have the same value. Across the columns, there was also inconsistent null value reporting, where sometimes empty fields would be denoted as an empty string, null, none, or nan. We also saw that some columns were overly packed with more than one value per field. For example, land cover classifications of a photo were listed as a dictionary in one column. This makes it very difficult to parse out key land cover classifications. Another problem we found was that some columns had a reasonably large number of decimals. For example, integers like user ID were stored as decimals. Similarly, certain latitude and longitude coordinates were stored with unreasonably high precision that is simply impossible to obtain with current GPS technology. Decimals take up a lot of memory, so we realized that we needed to round values appropriately. All of these aforementioned problems limit Globe datasets' accessibility and overall quality. So we came up with a few solutions. We removed and renamed columns appropriately, unpacked dense columns with more than one field entry, standardized null values, and appropriately rounded numerical data. We also built an attribution validation procedure where we flagged any entries with extremely extraneous values. For example, in the mosquito habitat mapper dataset, we flagged observations with extremely large larvae counts, like 10 to the 27. These quality assurance flags also included photo counts and other data-specific flags. For mosquito habitat mapper, we also flagged extraneous larvae count, whether the user identified a mosquito genus, if there was a reported water source, and other key metrics. For land cover, we also flagged whether users inputted land cover classifications for each direction. We also built in completeness scores that can help future users filter out visible data. As a future extension, we would allow users to weight specific parameters, which would better enable dataset personalization. Lastly, and perhaps most importantly, we built a giant metadata index for our dataset to note what each column meant, what was the data type, what were entries, and how we denoted extraneous or empty values. This helps future users better understand and use our data products. Overall, our solution increases the accessibility and usability of Globe's legacy ecological datasets, which can help drive future models.
Now, as we look to the future, there are a few things that we should keep in mind. We need to continue refining and updating our data cleanup and quality assurance procedures. As new citizen science standards arise, we need to update our procedures to match the current standard. We also need to continue following the PPSR citizen science metadata best practices. This will increase Globe Observer's dataset compatibility with other datasets. We also need to remain vigilant for new data peculiarities, refining our data validation procedures to flag additional and new extraneous entries. Our next steps are to enrich our Globe datasets with satellite measurements. Linking citizen science observations with the satellite perspective can help us develop more robust models for mosquito and ecological behavior. Here is an example of how users can filter out less useful data for their own specific scientific questions. Let's say a user is trying to build a machine learning model that classifies mosquito larvae from a photo. For this project, they would need to use observations with a larvae count greater than 0 and a photo count greater than 0. On the left, we have the raw mosquito habitat mapper data. As you can see in the top left larvae count distribution, there are many observations with a null larvae count, which we represent with a negative number. And in the bottom left, we see that there are also quite a few observations without any photographs. The user would want to remove these unusable entries. So with our pre-processing procedures, the user could download MHM observations with a positive larvae count and at least one photo. Now, if we look to the right, we get a visual verification that our filtering worked. The user now only has observations that he or she needs. There are no entries with extraneous larvae counts or no photos. Now the user can go and more easily build their machine learning model.
On the left, we have a multiple bar graph displaying the distribution of land cover photo statuses on a log scale. The different photo statuses include valid photos, rejected photos, and fields without photos. Since we had to use a log scale to better showcase the distribution, we see that our spread is extremely wide, highlighting that some users would greatly benefit from filtering out observations without valid photos. Below the bar graph, we have a histogram of mosquito habitat mapper completeness scores. This cumulative completeness score is the percentage of all MHM columns filled out by a specific observation. As seen in the graph, there's a high center and moderate spread in completeness, indicating the mosquito habitat mapper observations are mostly all filled out, but there is some diversity in observation completeness. If we look at the MHM completeness on a more global scale, we see here on the map that Globe MHM datasets are pretty diverse, both geographically and in terms of quality. And in this map, we can also see how large Globe Observer's reach really is. The organization samples from many diverse environments. Overall, Globe's mosquito habitat mapper and land cover datasets are not only rapidly growing in size, but also in applicability towards scientific research. Our data pre-processing protocols will help further the accessibility and usability of this data so that more researchers can use Globe datasets to explore unique scientific questions. If you are interested in contacting us further, please feel free to reach out to ourselves, Rusty, and Peter. And if you would like to learn more about the Globe Observer dataset or access Globe data, please visit these links to the Globe API and IGES portals. Thank you all for attending our presentation.